Hi, everyone. We're going to start chapter 3 now, and it has to do with ionic compounds. To be able to talk about ionic compounds, we have to first discuss what ions are. Ions are charged atoms in which the number of protons does not equal the number of electrons. Remember back in chapter 2, we learned that the atomic number for each element told us how many protons were in each atom. And that was where we start with the number of electrons as well. As long as an atom is neutral, the number of protons equals the number of electrons. But let's say we start playing around with the number of electrons, maybe gaining some or losing some. Then the number of protons will not equal the number of electrons, and the charges will change. It will no longer be the total positive charge canceling out the total negative charge. Now we'll have an imbalance, either more negative or less negative overall. There's two types of ions. There are cations and anions. Now, many of you will probably really like cats. So remembering that the positively charged ions are cations will be easy for you. For those of you who are not as big a fan, maybe this will help. Seeing a very silly cat with lots of positive signs around it to help you remember that cations are positive ions. The anions, boring name, anion, those are our negative ions. I did see something online where they were showing onions, kind of looks like anions, and how onions making you cry, so that's kind of negative. That might work for you too. Atoms and ions, they're stable if they form bonds with each other, unless they're already noble gases. And so we're also going to look in chapter 3 and chapter 4 about forming different types of bonds between atoms. And also we might form some bonds between ions. Elements and the atoms of those elements will gain, lose, or share valence electrons to get the same number of electrons as their nearest noble gas. And we'll talk about who the nearest noble gas is for the different elements, but the goal is to have the same number of valence electrons. Remember, those are the electrons farthest away from the nucleus. They're the ones involved in bonding. We will discuss two kinds of bonding: ionic bonds. Ionic bonds result from the transfer of electrons from one element to another, or one atom of an element to another atom of a different element. Covalent bonds result from the sharing of electrons between two atoms. Covalent bonds are discussed far more in chapter 4, but there's a little bit in chapter 3 that we want to go over, so that we'll start with covalent bonds for just a few minutes. Then we'll switch over to ionic bonds for the rest of the chapter. How do I know whether something's going to make an ionic bond or a covalent bond? I look at the periodic table. The position of an element in the periodic table determines the types of bonds it makes. So we'll be going over that as well, how you can use the periodic table to predict whether an element is going to make an ionic bond or covalent bond with another element. As a reminder, this will be important now that you really recall that there are three classes of elements. There are the metals, which most elements are metals. You have to know this. This is critical. So somewhere where you can view it often, it doesn't have to be a shower curtain like mine, but it does come in handy. You must know which ones are metals. You also need to know which ones are not metals. We talked about nonmetals and metalloids. When it comes to bonding, the metals will be different than the not metals. So nonmetals and metalloids will behave in a pretty similar way in these two chapters about bonding. Metals versus not metals. You need to know where an element is and which category it falls into. Like I said, we're going to talk just a little bit about covalent bonds in chapter 3, Then we'll return to them in chapter 4. Covalent bonds, co meaning to share, like a community or a co-op or cohabitating in the same home. Covalent, where we have the word valence for valence electrons. Covalent bonds are formed when two nonmetals combine or when a metalloid bonds to a nonmetal. Because again, the metalloids are very similar to the nonmetals when it comes to bonding. A molecule is a compound or element containing two or more atoms joined together with covalent bonds. So far, we've mostly just used the term compound or element or mixture. Molecule is just one additional term. Sometimes a compound is a molecule, sometimes an element is a molecule, but what will always be true is that a molecule is made from covalent bonds. We'll talk about them some more in chapter 4. You'll be asked to identify, based on the elements, whether they're making a covalent bond or an ionic bond. If they are nonmetals together or just metalloids and nonmetals, it'll be a covalent bond. The rest of the chapter is about ionic bonding. The ionic bonds form between a metal that's on the left side or middle of the periodic table and a nonmetal on the right side of the periodic table. Or don't forget little hydrogen, he's over there at the top of the first column, but he's still a nonmetal, and he will behave like every other nonmetal when it comes to ionic bonds. And here we have an example where sodium's an element in group 1A, all the way at the left, he's a metal, and chlorine is an element way over on the right in group 7. So with group 7A and 1A coming together, they will form an ionic bond, an ionic crystal. And this is a fantastic reaction. At some point, we'll take a look at it because the sodium metal can catch on fire if it's in water, and the chlorine gas is this toxic yellowish green gas, but you put them together and a little bit of a spark and boom, you get sodium chloride crystals. And those, of course, are sitting on our kitchen table right now, not catching on fire or poisoning us. Whew. Cations. Again, those are our positively charged ions. Cations have fewer electrons than protons. They've gotten rid of some of that negativity. So they've been zen. We have all of our positive cations with fewer electrons than protons. Metals always form cations. They're always going to lose electrons. Here we are with sodium again, and I see that he has 11 protons and 11 electrons to start with. If I didn't get told that, I could use the periodic table and see that his atomic number is 11. Then I'm going to guess that mass number for him, if it's 11 protons and 12 neutrons, this particular isotope of sodium must have an atomic mass of 23. Remember, the number of protons doesn't change. If the number of protons changes, it won't be sodium anymore. But the number of electrons can change. Sodium is a type of metal. Metals always lose electrons. They always form cations. In sodium's case, he loses one electron and becomes a sodium cation. By losing an electron, he became more positive. He now has a positive 1 charge. I want you to note again how an atom that loses an electron becomes an ion with a more positive charge. So the signs are backwards. I subtract an electron, I gain a positive charge. It's losing some of its negative attitude. And my t-shirt today, for my geeky shirt, I've been waiting to show you guys. My geeky shirt, the guy on this side says, I've lost an electron. And the other atom says, oh, are you positive? Okay, I can hear you guys all laughing through the ether. Yes, okay. So that's my geeky joke for today. And I'll be honest, that's going to probably be the quiz question for participation, knowing that I've lost an electron and the other atom saying, are you positive? That's going to be our joke and our quiz question for participation this time. All right, so what happens next? Well, we're still talking about cations with those positive charges, and we know that by losing 1, 2, 3 electrons, heck, I've even seen some lose up to 5 electrons. Many metal atoms can form cations with the same number of electrons as a noble gas. And I mean, noble, the nobility, the kings and queens, they are the ones that have the coolest party, the coolest stuff. And so everybody wants to go to the same parties as the noble gases. But to get in, they have to have the same total number of electrons as the noble gases. Here we have a magnesium atom. It starts out neutral with 12 protons and 12 electrons. Atomic number must be 12. Magnesium loses 2 electrons. Now he has a positive 2 charge. One thing you may notice as I'm going through, when I tell you charges, even if it's just one, you're going to hear me always say whether it's positive or negative, and you're going to hear me say a number. Sodium became positive 1 charge. Magnesium, another metal, has a positive 2 charge. The noble gas, which can be called the nearest noble gas, will be in the last column of the previous row of the periodic table for our metals. When we look for the nearest noble gas for metals, we're going to go up a row and then check out who's in group 8A. Let's take a look at a periodic table. We're going to look for the nearest noble gas for magnesium. Magnesium's way over here in group 2A on the left-hand side. There's his atomic number 12. If he loses 2 electrons, the first one he gets down to 11 electrons like sodium, and the next one he loses will get him down to 10 electrons like neon. Group 8A, over here on the right-hand side, these are our nearest noble gases. Whoops. So the nearest noble gas for magnesium is up 1 row in the last column. The nearest noble gas for magnesium is neon. Well, what about sodium? We saw that he loses 1 electron. He goes from starting with 11 down to 10. Well, look at that. His nearest noble gas is also neon. Now that magnesium and sodium have lost their electrons and they're down to 10 electrons, they can go to the cool parties with the other noble gases. Remember that metals always lose electrons, so we're always going to go up a row when we look for their nearest noble gas. Anions. They're the negatively charged ions. An anion has more electrons than protons. That's what gives it a negative charge. So remember, if I add an electron, I get a negative charge. The signs are opposite of what you might think. Non-metals form anions. Metals form cations. Non-metals form anions. Here we start with a neutral chlorine atom. 17 protons, 17 electrons. His atomic number is 17. He's going to gain 1 electron. That will then give him 18 electrons. Well, he's only got 17 positive charges. Each proton is a +1 charge. With 17 of those, he has 17 positive charges inside his nucleus. If he gains an extra electron, he has 18 electrons. That's a negative charge of 18. So he has an overall charge of -1. Do I have it written down? Nope. I just have it written down that you should note how an atom that gains an electron becomes an ion with a more negative charge. It gains a -1 charge because each electron has a -1 charge. The number of protons didn't change, and we're not talking about isotopes anymore, so the number of neutrons aren't going to change either. When we talk about ions and ionic bonding, we're just going to be looking at electrons. Well, we've got some tricks. Remember with the valence electrons, you learned that you could look at the group number for groups 1A through 8A, and whatever the group number was, that told us the number of valence electrons. We're going to keep using that idea. That was why it was so important that you learned that the shortcut for knowing the number of valence electrons is to look at the group number, as long as it's in groups 1A through 8A. Well, elements in the same group, so the same column, will form ions with the same charge. And why would that be? Elements in the same group have the same number of valence electrons. They will want to lose or gain the same number of electrons to be like their nearest noble gases. So everybody in group 1A will want to lose 1 electron, just like sodium did, to be like his nearest noble gas. Metals always lose electrons to form positive cations. Metals are most of the elements on the periodic table, from the left 2 columns through the middle, down at the far bottom, and a little bit off to the right-hand side too. Things like tin and lead, those are still metals. For ions of metals in groups 1A, 2A, and we usually talk about aluminum over there in group 3A, their positive charge number equals their group number. Metals in groups 1A, 2A, and 3A, the positive charge number equals the group number. Metal ions will have the same number of electrons as the noble gas in the previous row. We looked up 1 row when we had a sodium ion and a magnesium ion. We do the same thing for all of the metal ions. So here we have the examples. Here are the elements that are in group 1A. Each one of them will lose 1 electron and get a +1 charge. This only shows the plus sign. The 1 is invisible. You can also write the 1, we just typically don't, but the 1 is there. Let's see what happens. Lithium starts out with 3 electrons. If he loses 1, he's down to 2. Okay, well, if I go up a row and off to the right, there's helium, the noble gas, with 2 electrons. He's lithium's nearest noble gas. We already said sodium's nearest noble gas was neon. How about potassium? He starts with 19 total electrons. If he loses 1, which is what he'll do in group 1A, then he'll be down to 18 electrons. Well, let's take a look. Which element has 18 electrons? Oh, argon. Over here in group 8A, yet another nearest noble gas. That's the nearest noble gas for potassium, number 19. And we see that everybody in group 2A follows the same pattern. They lose 2 valence electrons so that they can be like their nearest noble gas. Let's see, calcium. He's right next to potassium. If he loses 2 electrons, he gets a +2 charge. And now he also has the same total number of electrons as argon. They're headed to that cool party with the other noble gases. We're not going to worry about these guys here in number 3 because they're not one of the group A's. They're not the 1A through 8A. We do want to take a look at aluminum though. Aluminum is right here in group 3A. It's also number 13, but group 3A, he will lose 3 electrons. He'll lose his 3 valence electrons that he has being in group 3A. When he does that, he'll have a +3 charge, and he will have the same total number of electrons as neon. Notice the pattern that they put the 3 and then the plus sign. If you put +3, that is just fine. You can put 2 and then the plus sign, or you can put +2. Either one's the same. We still say +2, no matter which direction it's written. A trick to remember that metals always form positive ions, if I haven't said it enough yet, you think how you will feel positive when someone gives you some gold or silver or metal. So remember your good old gold AU, bring me back my gold necklace, or maybe somebody gave you some silver and you're like, hey, or copper. Those are all going to form positive ions. Nonmetals will form negative ions when they're with metals. When they hang out with metals, that's going to happen. Their negative charge equals 8 minus the group number. Or you can count the boxes if you're looking at a periodic table. You go with the element, and then you count over in the same row to the nearest noble gas. So for negative charges for our nonmetals, and it works with metalloids too, we count the number of boxes to the right in the same row because they are adding electrons. All right, good old hydrogen. When hydrogen's with a metal, he will gain 1 electron and be hydrogen with a -1 charge. When he gains the electron, he has the same total number as helium. In group 5A, we have nitrogen and phosphorus. Those guys are 1, 2, 3 columns away from their nearest noble gas. So they will gain 3 electrons. Another way to see that is 8 minus the group number 5 equals 3. So these guys in group 5A will form a -3 charge. The ones in group 6A, oxygen, sulfur, selenium, these guys are 2 groups away from the noble gases. They'll gain 2 electrons. Oxygen will go from having 8 total electrons to having 10 total electrons, just like neon. Sulfur starts with 16, comes near a metal, or maybe more than 1 metal atom. They give them electrons, and now he's up to sulfur with a -2 charge and the same total number of electrons as argon, who's in his same row. And here they put it all together. Lithium, sodium, potassium, everybody in group 1A makes a +1 charge if they're a metal. Everybody in group 2A, they are making a +2 charge. Aluminum is in group 3A, he makes a +3 charge. Then we cross the zigzag line, so we're into the metalloids, and then over here, we're in the nonmetals. So now we're going to gain electrons. Group 5A gains 3 electrons. Group 6A, 8 minus 6 is going to be a 2. So these guys in 6A have a -2 charge. And everybody over here in group 7A, my halogens, they all have a -1 charge. In the chapter of the textbook, they do talk about cations of metals that have variable charges. So some transition metals, for example, can form cations like other metals, but the size of the charge, for example, whether it's +2 or +3, well, determining that, it's harder to predict. Some transition metals form only one type of cation. The 2 that we're going to use the most are zinc, who has a +2 charge, and silver, who has a +1 charge. A mnemonic trick, memory trick for you. You know aluminum in group 3A will always have a positive 3 charge. Look at a downward staircase. Here we have zinc, one box to the left and down. He will always have a +2 charge. Come one more spot down on the diagonal, there's silver, always has a +1 charge. So +3 to start with because he's in group 3A. Zinc and silver also have known charges, even though they're not in one of the group A columns. You need to know those 2 charges. I'm going to assume, and everyone else will assume, that you know that zinc is +2 and silver is +1. We can't look at where they are on the periodic table necessarily to figure that out. That's something that I need you to just know, have it written down somewhere. Some metals form more than one type of cation. For example, iron can make iron +2 or iron +3. The names of those compounds that include metals that can make different size charges, their names include Roman numerals. So that's like the I, the IV, the VII. We may see these compounds in lab, and you may come across them in the textbook, or I tried to make it so none of the assignments will have that. We're probably not going to discuss them further in lecture. I just want you to be aware that there are multiple cation forms for some metals. So again, chromium commonly makes +2 or +3. Just depends on who he's hanging out with and what kind of compound they want to make that day. Some common ions in the human body. Calcium is found in our teeth and bones, incredibly important for nerve transmission, making our muscles move. They all need calcium ions. Sodium and potassium, those guys are found in all our body fluids. Very important for, again, electrical signals like making our nerves go and making our muscles work. Iron, 2+, it's not just the metal iron, it's an ion of it. That's present in our hemoglobin of our blood. That helps with transporting oxygen. Chloride is present in the gastric juices of the stomach and other fluids. So that acid reflux you're getting, that's from hydrochloric acid. There's a chloride ion hanging out in your stomach. I want you to memorize about calcium 2+, iron 2+, sodium +1, and potassium +1. I need you to know where those guys are found commonly in the human body based on just this chart, not what I just said, but what's in the chart. Lastly, magnesium, calcium, sodium, potassium, they're all needed for our nerve signals to go through and for our muscle control. A little bit about the sodium ion. I don't know if I realized this was in the textbook when I made this last semester, because I just came across it today when I was looking over the chapter again. Although sodium ion is an essential mineral needed in the daily diet, the average American consumes 3 to 5 times the recommended daily allowance, which is capitals RDA, of 2,400 milligrams. Excess sodium intake is linked to high blood pressure and heart disease. Maybe that's why my blood pressure was high yesterday. Dietary sodium ion comes from salt, sodium chloride, that's added during cooking or at the table. Sodium ion is also added during the preparation of processed foods and canned products. For example, one 3.5 ounce serving of fresh asparagus has only 1 milligram of sodium, but the same serving size of canned asparagus contains 236 milligrams of the sodium ion. We need to find out, well, I want you to find out, how many protons and electrons are in an atom of sodium, and how many protons and electrons are in the cation, sodium +1, and who is sodium's nearest noble gas. I'm going to pause the recording. I want you guys to work on these answers, and then when I come back, I'll be on my doc cam so we can go through the answers together. All right, let's take a look at this problem. I'm using the periodic table to find sodium, and I see that his atomic number is 11. What does this tell me? Well, when he's neutral, which I assume everybody on the periodic table is to start with, how many protons does he have? He starts with 11 as well. The number of electrons, if it's neutral, he'll have 11 electrons as well. Okay, now we're looking for a sodium ion. So the number of electrons is going to change. Well, it's still sodium, so the number of protons still has to be 11. He is in group 1A, and sodium is a metal. Metals always lose electrons. In group 1A, they always lose 1 electron. Starts with 11, loses 1, so now he has 10 electrons. His total positive charge is positive 11. His total negative charge is negative 10. 11 minus 10 is equal to a positive 1 charge on the ion. What's the nearest noble gas for sodium? Here he is, he's in the third row. 1, 2, 3. I'm going to go up a row and all the way over to the right where the noble gases are. When sodium has 10 electrons, he's like neon. The nearest noble gas for sodium is neon. The total number of electrons neon has is also 10. So sodium plus 1 and neon have the same number of electrons. Yay! Let's head off to the party together. Let's do another one together. How about we do strontium? He's way down here. So we've got strontium. And his atomic number, or SR, his atomic number is 38. When he's neutral, he's got 38 protons and 38 electrons. He's also in group 2A, a metal in group 2A loses 2 electrons. Strontium becomes a +2, or we can write it as strontium +2 ion, cation to be specific. Group 2A makes +2. Who's his nearest noble gas? Strontium is in 1, 2, 3, 4, 5. Strontium is in the 5th row. The nearest noble gas will be in the 4th row. How many total electrons is it going to have? Well, it needs to be the same number as the strontium ion. So this one is going to have only 36 electrons. It started with 38 because the atomic number was 38. Strontium's in group 2A, so he loses 2 electrons. That leaves him with 36 electrons total. The nearest noble gas will be in the 4th row, and the atomic number will equal 36. And that's because it will have 36 electrons. Don't believe me? Well, let's check. Here we go. We'll look at the periodic table. There he is, krypton, 36. Strontium in group 5, row 5, group 2A. His nearest noble gas is krypton. In the 4th row, group 8A. I hope this has helped. It's important that you be able to figure out the charges on all your elements and to understand that they're trying to be like the nearest noble gas. For metals, it's the previous row. For nonmetals, it's the same row. All right, it's time for us to bond. We're going to talk some now about chemical bonding. A chemical bond is a strong force of attraction between 2 atoms or 2 ions in a molecule or compound. When a positively charged ion, what was that called again? Try to think of the smiling cat. It's a cation. When it's attracted to a negatively charged ion called I'm going to stutter a little bit, an anion, they form what type of bond? Do you think it's going to be an ionic bond or a covalent bond? Well, heck, we're talking about ions, so it has to be an ionic bond. The sharing of electrons, that's when we have 2 neutral atoms. They're going to share electrons. They're sharing valence electrons, so that's the covalent bond. And remember, we find those when we have things that are not a metal. The nonmetals or the metalloids bonding together make covalent bonds. Here is what's really, really important. How to recognize whether a compound is ionic or covalent. There's going to be a ton of material based on whether you can look at a name or a formula for a compound and know if it's ionic or covalent. I cannot stress this enough, how important it is to be able to do this. So what I did was I came up with only 2 ways to be ionic. Either it will have a metal in it. So again, you have to know which elements are metals. Or it's going to have something known as ammonium. This is going to be a collection of a nitrogen and 4 hydrogen atoms that are bonded together. It has a special name and a special charge. We're going to learn more about it soon, but not just yet. I wanted this to be in one easy box for you, though, where you'll always be able to refer to it. Given a name or a formula for compound, I will automatically be checking, does it have a metal or does it have ammonium and NH4? If so, it's ionic. The metal or the ammonium cation, metal cations, ammonium cations, they will have a positive charge. That's going to be strongly attracted to the anions with negative charges. Good old opposites attract. We already learned about why electrons stay in an atom. It's because they're attracted to the positively charged protons in the nucleus. Well, now we're finding out that if we have an entire atom with a positive or negative charge, that will also be attracted to another atom or ion with a negative charge. That attraction is known as an ionic bond. And we will talk a little bit now, but also again, when we do the lab, the next lab, we're going to be talking about how that's a really strong connection between positive ions and negative ions. It's actually a stronger force of attraction than what we find with covalent bonding. When we start making these ionic compounds, we have to keep in mind that when we add up the charges in an ionic compound, it must equal 0. The total must be 0. So here we have a sodium with a +1 charge. He is being attracted to a chloride ion with a -1 charge. +1, -1, they cancel out, and we have a neutral 0 for our ionic compound for sodium chloride. +1 ions, -1 ions, 1 to 1, 0 total charge. Here we're working with calcium and fluoride. So we have the calcium ion. He's in group 2A. How did I know that? How did I look at this and immediately know the calcium's in group 2A? Oh, because everybody in group 2A forms a +2 charge. Okay, so now each of these fluoride ions, they came from fluorine, they gained 1 electron. So what group would they be in if they only needed to gain 1 electron to be like the noble gases in group 8A? What group is fluorine in to gain 1 electron to reach the guys in 8A? Right, he's in group 7A. Fluorine's in group 7A. He gains that 1 electron, so now he gets to go to cool parties like neon. Now they'll have the same number of electrons. But the calcium is sitting there with a +2 charge. I can't make an ionic compound that has an overall positive or negative charge. So if he's only going to come into contact with fluorine atoms, he better find 2 to interact with. Those 2 fluorine atoms will take electrons away from the calcium. Now calcium's happy, he's a positively charged cation. Those fluorine atoms that now have a negative charge, they're happy, and they're going to be attracted to each other. It'll be a ratio of 1 calcium ion to 2 fluorine ions. Fluorine ions are known as fluoride ions. 1 to 2 ratio. That's because the 1 calcium ion has a +2 charge. We need to cancel it out with 2 -1 charges. Then we can have a 0 overall charge. There's more examples of this on page 89. And remember, you can still see the ebook. If you don't have the hard copy, just go on to Connect and it says read, and you can go to that and you can tell it to go to page 89 to see some more examples. We're going to go over how to write the formula for an ionic compound. Before you can do anything, you're going to have to know which element is the cation and which is the anion. Well, this is the same as saying which one's the metal and which one's the non-metal or not a metal. K is all the way on the left-hand side. He's over there with sodium. So he's in group 1A. Is he going to be a metal and make a cation, or is he a non-metal and makes an anion? Group 1A, those are our metals, our alkali metals. So he's going to form a cation. What about Cl? He's right underneath fluorine over in group 7A. What does that make him? Metal or non-metal? Non-metal. So he's going to form an anion. Metal, non-metal. Calcium's in group 2A. That makes him a metal. Oxygen's way over on the right in group 6A. Oxygen is a non-metal. Now, we're going to use the group number for each of these guys. They're all main group elements to determine their charges. Potassium's in group 1A. He will have the same size charge. The main group metal charges equal their group number. The non-metal charges, we're going to take the group number and subtract it from 8. So group 1A, potassium will be a +1 charge. Chlorine is in group 7A. So the chloride ion, 8 minus 7, he'll have a -1 charge. Calcium, group 2A, will have a +2 charge. Oxygen is in group 6A. 8 minus 6 is 2, so he will have a -2 charge. All those guys in group 6A have a -2 charge. They're 2 electrons away from their nearest noble gas. Now, to write the formula for the ionic compound, we need to determine how many of each ion type is needed for an overall charge of 0. Remember back with sodium and chloride? Sodium was +1, chloride was -1, so it was just 1 to 1. When the cation and the anion have the same size charge, obviously one will be positive and one will be negative, but if the number is the same, only one of each is needed. They balance out. So K with a +1, chloride with a -1, we just need one of each. There are invisible 1 subscripts down here. So it's a ratio of 1 to 1. We have a neutral compound. With calcium, he's +2. Oxygen forms -2 ions. They balance out. +2 minus 2 adds up to 0. So we end up with our neutral ionic compound. When they have the same size charge, only one of each is needed. I want you to be careful when you're working backwards. I want you to use the table for charges. A big mistake that people make a lot is they see that this is 1 to 1, and so they tell me that calcium has a +1 charge and oxygen has a -1 charge, but that's not true. We use the periodic table to check and see, oh, calcium's in group 2A, so he's +2. Oxygen's in group 6A, so he's -2. Use the periodic table for charges. And I'm going to go ahead right now while we're still working on this, and I'm going to type in the word same size charge. All right, so the same number. And we're going to go back to this for a second. There we go. I'm going to get rid of the black box at the bottom. And okay, so this is what we said. Same size charge, one of each. Use the periodic table if you're given the formula and have to figure out the charges on the ions. What if it's not the same size charge? Well, when the charges aren't equal sizes, you can use the crisscross method. The cation's charge becomes the subscript, the little number on the bottom right, for the anion, and vice versa. So here I have magnesium in group 2A. His charge is +2. The bromide ion, bromine's in group 7A, so his charge is -1. We will crisscross the 2 and the 1. Now, the subscript for magnesium is the 1 that was the charge for bromine. The subscript 2 came from the number 2 in magnesium's charge, the crisscross method. It's important that only the numbers cross, not the charges. The positive signs and negative signs, they only go in the upper right for our ions. We won't see any numbers in the upper right for compounds because they're all neutral. And we don't have any pluses or minuses down here. They're just numbers to tell us the number of ions. Well, what ionic compound is formed when aluminum in group 3A reacts with oxygen in group 6A? We're going to write the cation symbol first and the anion symbol second. Well, aluminum's the metal, so he goes first. He will be a positive cation because metals are always positively charged cations. Oxygen is a nonmetal, so he will have a negative charge. He will be our anion. Now we need to determine the charges on both ions. Aluminum's in group 3A, so his charge will be positive 3. Oxygen's in group 6A. 6 and 8, difference is 2. So oxygen has a negative 2 charge. They're not the same, are they? Plus 3 for aluminum, minus 2 for oxygen. It won't be just 1 to 1. We need to crisscross. Since the charges aren't the same, use the crisscross method. The aluminum, his 3 will become the subscript for the O. The 2 in the charge of oxygen will become the subscript for the aluminum. Think about what that's going to look like after we do the crisscross. Is that what you got? Al subscript 2, because the charge on oxygen is minus 2. O3, because the charge on aluminum is plus 3. To write the formula, you place the cation first and then the anion. Do not include their charges. KCl, 1 to 1. Calcium oxide, 1 to 1. Magnesium bromide, we have 1 magnesium and 2 bromide ions. All of these is to get a neutral ionic compound. We use subscripts to show the number of each ion needed to have a 0 overall charge. When no subscript is written, it's assumed to be 1. If I wrote it down, I know we have to have 1 of it. Naming them from their formulas. What's important? Well, the metals from groups 1A, group 2A, aluminum in group 3A, zinc, and silver make only one type of ion. These guys are not like the other metals we talked about that can form +2 and +3 or +1 and +3. These guys, everyone knows their charges. It doesn't change for any of these metals. So when everyone knows their charges, we don't have to include the charges in the names of the compounds. You don't need to know how to name the metals with variable charges like iron. We're not doing that in this course. It's in your textbook. So if you read the chapter in your textbook, you'll learn about how to do that. But we're not going to do that for this class. The metals whose cations always have the same charge are named just for the element from which they're formed. So the sodium ion, his name is sodium. Aluminum's in group 3A +3, his name's aluminum. Remember that little diagonal side staircase thing? Zinc was the next guy down. He's always +2. We just call him zinc. And Ag +1, he's just called silver. I'll be honest with you, lots of times I can tell who's been doing stuff looking on the internet because they'll put silver and then the Roman numeral 1 and then the ion. The deal is silver's always +1. I haven't come across a compound yet where silver was not +1. So I can tell if you've been Googling because you'll come up with answers that have the Roman numeral 1 in them. But in this class, he's just always +1. You don't need a Roman numeral for silver. Naming anions. Anions that are only one element. Replace the end of the element name with IDE. On page 92, table 3.3, you have the names of the common anions. Bromine, chlorine, fluorine, iodine, those guys are easy. They just become bromide, chloride, fluoride, iodide. Then we have the gens. So nitrogen becomes nitride. Oxygen becomes oxide. Then phosphorus and sulfur, phosphide, sulfide. You'll get better as you do more and more of these problems and practice naming. You'll get better at changing a name like oxygen to oxide. Let's name some ionic compounds. To go from the formula to the name, you must ask first, is the compound ionic or covalent? Because just because we're only looking at ionic compounds in chapter 3, you're going to see covalent compounds in chapter 4, You're going to learn how to name them. And then on the test, you're going to have to name a mixture of ionic compounds and covalent compounds. You've got to be able to look at them and say, is it ionic? Then I'm going to name it this way. Is it covalent? I'm going to name it this way. They have different ways of naming depending on whether they're ionic or covalent. So let's identify it. To figure it out, look to see if it has a metal element in it or if it had that ammonium in it, the NH4. If it does, it's an ionic compound. Once you've determined that it's ionic, you need to name the cation and the anion. The cation always comes first. I want you to remember the special endings for the anion names. If it's one element, it ends with IDE. So here we have the sodium ion. The fluorine has become fluoride by gaining an extra electron. Together, they make sodium fluoride. What's the name for magnesium? What's the name for MgCl2? Okay, so you might need to go to the periodic table and look up what Mg is. Or you might have just heard me say it. Remember way back in chapter 2 when I said that if you see this arrangement here with the C and the straight next line next to them, 99% of the time that's going to be an L, not an I. So I know the anion in this particular compound is Cl. Well, let's determine if the compound is ionic or covalent. Is there a metal in it? Did you find Mg on a periodic table? He's over in group 2A. So that makes him a metal. We have a metal, so we're ionic. Then we're going to name the cation and the anion. Mg is magnesium. Chlorine becomes chloride. Magnesium and chloride, magnesium chloride. There's no charges in the name. There's nowhere where I say magnesium 2, chloride 1. And there's no number of ions in the name. We know how to make it by doing the crisscross method. So we don't need to tell anybody how many of each ion we have. I don't have to tell people the charge number, and I don't have to tell them that there's 1 magnesium and 2 chlorides. That's something we can figure out by doing the crisscross with their charges. All right, we're getting near the end. This is the polyatomic ions part. A polyatomic ion is a cation with a positive charge or an anion with a negative charge overall. It contains more than one atom though. Poly meaning many, atoms, polyatomic ion. Here's the deal with these. These guys all have special names and special charges. I cannot look at the periodic table to find out the names or charges of polyatomic ions. You must use the Polyatomic Ion Table. That's something that I've got for you on Moodle. I've posted it there. You really probably want to have that printed out. You're going to want to be able to look it over a lot. If you can't print it out, then I recommend recopying it down. Heck, you could recopy it down anyway, just so that you work your way through it and practice the different formulas with their charges and their special names. This one from table 3.4 has the ones from the book, and it's highlighted some of the more popular ones. The one that we're going to use in class has all of these and maybe a few more. All of them have more than one element in them. And you know what? I'm going to change that too. We're going to say that it's more than one element in it too. So let's change this. More than one element. Okay. And we will go back and see it full screen and get rid of the box. What are some other ones? You might have heard of cyanide. Well, there's our cyanide, Cn with a -1 charge. And hydroxide, we'll talk about him a lot, especially again when we do acids and bases. One thing you'll notice in the chart and here, they're putting the negative sign at the end. The way I write it, the negative sign will go next to the oxygen, and up here, the negative sign will go next to the carbon. That's just because those are the atoms that have the negative charge on them. But either way is fine. When you write formulas for ionic compounds that contain polyatomic ions, the same as before, when a cation and anion with equal charges combine, we only need one of each. Here we have the sodium ion, and we use the chart to see this guy, NO2 with a -1 charge. If I put those guys together, the +1 and the -1 cancel out, so I only need one of each. The nitrogen and the two oxygens must stay together. They are one unit. Those atoms are bonded together, so they're going to move as one unit. Together, the nitrogen and two oxygens have a total -1 charge. Barium in group 2A is combining with the sulfate ion. Sulfate ions have one sulfur and 4 oxygens that are bonded together. They move as one unit. That unit has a -2 charge overall. Well, if I hook them up with barium, I only need one of each. The charges cancel out. We have a neutral ionic compound. So I want you to think about the fact that the atoms in a polyatomic ion stay together as one unit. So you can treat them as regular ions. The NO2 with a -1 charge behaves just like one fluorine ion with a negative charge. The sulfate group with a -2 charge, it behaves just like an oxygen ion with a -2 charge. There's just one difference. When they have more than one polyatomic ion, we have to do something special. So like before, when a cation and anion with unequal charges combine, you need to use the ionic charges to determine the ratio of the ions in the compound. You use the crisscross method to determine the subscripts. Magnesium is +2. Let's put them with hydroxide. Do you remember the formula for hydroxide yet? It's okay. It's OH with a -1 charge. And again, I put it on the left. Books sometimes put it on the right. Either way is okay. It's not the same this time. It can't be 1-to-1 because he has a +2 charge, but this is only a -1. It won't be neutral. So let's crisscross the numbers. The -1 for the hydroxide will become the subscript for the magnesium. We need 2 hydroxide ions. Well, we have to use parentheses if more than one of the polyatomic ions are needed in the ionic compound. Without the parentheses, for example here, if I just had MgOH2, the oxygen would have a subscript of 1 and the hydrogen would have a subscript of 2. That's not the same as saying that you have 2 groups of OH bonded together. So we use the parentheses around the OH, and then we put a 2 on the outside. Make sure you use those parentheses if you have more than one polyatomic ion. You don't need them around guys like magnesium. When it's in one element, you don't need parentheses, just if there's more than one polyatomic ion. The naming, same as before. You name the cation and the anion. If it's just one element, like just sulfur or just oxygen, the name ends with "ide." If it's more than one element, it's polyatomic, and you need to use the chart for the special name. You don't specify the charge on the cation or the anion. So here I have NaHCO3. I'm going to pause the recording and I'm going to open up the chart that you have access to on Moodle. And that's a chart that you get to use for the test as well. Here we are, the Polyatomic Ion Table that I recommend that you print out. It's got lots of good polyatomic ions on here. We'll be using many of the same ones over and over again. And the names change. Some end with ATE, some end with ITE. There's only a couple that end with IDE, well, 3, well, 4, look at that. So a few end with IDE. You'll need to check then. If you see the name of a compound and say it ends with sulfide, hopefully you'll recognize that that's just one element, that's just a sulfur. But if it's sulfate or sulfite, then you'll know it's more than one atom, more than one element, and you need to look it up on the periodic table. The hydroxide is 2 elements in it, even though the name ends with IDE. There is no hydroxygen element, for example. The one in the problem that we were just looking at, if I come back to this, was NaHCO3. So the Na we get from the periodic table, that's sodium. The HCO3, we look at our our polyatomic ion chart. The table, let's see. HCO3, there he is, hydrogen carbonate. And I see a star there, an asterisk. Let's look down here and see what it says. With one asterisk, it says, the common name for this ion is bicarbonate, sodium bicarbonate. You may have heard of that. That's baking soda. So you might have some in your fridge or freezer right now to keep them smelling fresh. The sodium bicarbonate, like Arm & Hammer, yeah, it absorbs bad smells. So it's a handy one to use in refrigerators, freezers, and shoes. Okay, so 2 names possible for HCO3 with a -1 charge. I recommend memorizing the polyatomic cation ammonium. Why do I do that? Well, we're looking for our cations in the formulas or names to see if a compound is ionic or covalent. And we look for a metal or ammonium to know that it's ionic. We have another example here, which I can already see the name for it, but let's take a look at this other guy. Al2, I recognize aluminum. Again, there is no AI, it's just Al2. And then SO4. Notice how it's in parentheses because there's more than one sulfate. SO4 group. There's 3 of them, so it has to be put into parentheses. Here, it's not in parentheses because we only needed 1 of this group. SO4. All right, we take a look at our polyatomic ion chart, and that's over here. I'm really bad at keeping secrets, aren't I? SO4 is sulfate. This is not something you can use the periodic table for. You've got to look at the polyatomic ion table to know that SO4 always has a -2 charge, and it's always called sulfate. All right, back to this again. We'll make it big again. And what else do we have left? Memorize ammonium. Almost done. Thank you for hanging out with me for so long. I appreciate it. Let's finish up with physical properties of ionic compounds. This is somewhere, page 96, I think. So I went through all the naming stuff and writing formulas first. This is located in the middle of the chapter, I think. What are some physical properties? Ionic compounds are crystals. They're crystalline solids at room temperature. So that's one thing that's really key to know. You remember when I said that all metals are solids at room temperature except for mercury? All ionic compounds are solids at room temperature. And that helps me remember that ionic compounds have metals. Metals are solids, ionic compounds are solids at room temperature. They have very high melting points. The one for sodium chloride is 801 degrees Celsius. Water boils at 100 degrees Celsius. And they also have extremely high boiling points. His boiling point is 1,413 degrees Celsius. It's crazy high. And we'll talk some more about this in lab. The fact that the positive ions and the negative ions, they're so much attracted to each other that to try to get them apart using heat is very hard to do. And that's what has to happen. They have to start moving instead of being locked in place with each other. To go from the solid state to the liquid state, they have to stop being so rigid with each other. And then, of course, to go from the liquid to the gas state, they have to really, really be pulled apart, despite thinking that, the other guy's just super sexy with that opposite charge. One other thing from this chapter, with the ionic compounds, when they dissolve in water, this is really cool. Because even though it's really hard to get them to pull apart the ions when they're dry, if you put them into water, a lot of these ionic compounds will separate into their positive ions and negative ions. If that happens, or even if it only happens a little bit, the solutions that they make, they're known as aqueous solutions because of water, they will conduct an electric current. So this is why if I'm standing in pure water and I get hit with electricity, it's not as dangerous as if I'm standing in salt water and I get hit with lightning. The electricity will move through the water that has salt ions in it, sodium and chloride ions. That's going to be a big piece also from lab, where we're going to look at other ionic compounds and covalent compounds, that's how ionic compounds can conduct an electric current when they're in water. My sodium chloride, I put him in water and he breaks apart. We're going to learn this term dissociates. He breaks apart into sodium ions and chloride ions. And that's just a really cool thing about water, that he's able to get and wiggle his way in and separate and surround these opposite charged ions and break them apart when he dissolves them. The health and medicine piece for this, ionic compounds are the active ingredients in several over-the-counter drugs. Calcium carbonate is the antacid in Tums. Magnesium hydroxide, that's an active component in Maalox. Iron Roman numeral 2, so again, you don't have to write that, but I'm telling you which iron ion it is. Iron 2 sulfate, FeSO4, that's an iron supplement used to treat anemia. And chemistry is like cooking, just don't lick the spoon. The ionic compounds perform useful functions in several foods. Potassium phosphate, K3PO4, that's a food additive. Magnesium sulfate is added to purified water, and sodium sulfite is a preservative. It helps extend the length that the food is still okay to eat. And that way I'm bringing in some culinary arts. Can't say I didn't try to include everybody. Whew. This was a long chapter. That was a lot of material. I tried to go through it slowly. I'll make a note to people that they can speed up the talking speed, but that was it. And hopefully you watched and saw pretty close to the beginning what the code was about this time, or what the thing is that's going to be on the participation quiz. If you missed it, start back over with the recording until you come across it again. It won't hurt you to watch it a second time. Okay,